make things completely concrete, here is a canonical hello world program. It's a hello whole world program. When you start your computation, like Java, you start it by telling the system on a command line, here's the name of the class whose main method needs to be executed. And that main method is executed in a single activity running at place 0. When you can specify with command line parameters how many places this calculation is to be run and the mapping of those places to nodes in your system. So having done that, now when your code starts running, this is the piece of code that's going to run. And I'm going to read this inside out. At the bottom, what's going to happen is, of course, you're going to print out some text that says, I'm running at this place P, and you print out value passed in from an argument in a lexically enclosing environment. So, and this statement though, you're going to run this statement at a particular place P. So you specify that by just enclosing an at, and you want to do this asynchronously because you want to do a lot of these. So you wrap it in an async. You want to do this at every place, so you put a sequential for loop around it that says please go to every place and do this. And then you want to wait until all of this is done so that you can terminate, so you put a finish around it. Now let's go back down from the top. The activity enters this guy, it spawns a finish that says something like, okay, I'm going to now track all the activities that are launched during the execution of this, enters a sequential for loop, in its body simply spawns asyncs, goes on and does the next thing. Each of these asyncs in its turn is simply a message sent to a remote place. And importantly, the message sent references a variable that's declared outside, so actually there is a copy of that thing happening when you transfer across this at boundary, and the system does all the serialization and does all the copying for you. There's a way to control the serialization, but at the top level you can do nothing, and this will do the right thing for you. So that's how this works. Now, of course, there are a lot more programs that we can write than just hello world. Go ahead.
Can S change?
Good. So that, let me address that. So the question is, can S change? So of course S can change. Well, in general, S is an array of strings. Arrays are mutable, so you can change S. So you could be spawning after this for another activity that is mutating S. Now, the X10 global object model prescribes that what happens is that when you get into at and go across the other side, a copy is made of this object over to the remote side at the time that that at is launched. So that's the state that you get. And now you can go mutate this S. That mutation is happening only locally in place 0. Those remote copies do not see it. There is a way of getting a so-called global reference to mutable state at a particular place, and for that, I don't have time to go to the details, let me just say something called global ref. And if you wrap this guy in a global ref, then what you get is a reference to on the remote side. You don't get a copy of its contents, and that reference now if you want to use, you have to async and at back to the place where the object was created, and now you will see its mutated state. So that's how shared mutation works. Yes?
Will it copy the whole array?
Good question.
Just the one?
So as far as the language model is concerned, semantics is concerned, the only thing you're guaranteed is that any value that is referenced in this code, it was declared outside, it will get copied. And will get copied deeply. So this may contain a reference to other objects and so on. In this case, it does not at all get copied deeply. Now there's obvious scope for performance improvement that says, let's actually analyze the body of this code and see what is really needed on the other side and send only that. And Vivek's group has been working on this, and we have papers.
Yeah, with Dave Grove and Igor.
Yeah. Dave Grove talking about this optimization and so on. So maybe when one of you guys speaks, you can give a reference to what that paper is.
Sure.
Yeah. Okay. Any other questions on this slide? Okay. So, that's a hello world program. So what you can do with the stuff that I've shown you so far is clearly you can go write the so-called SPMD style distributed programs. NPI style programs where at the very top you launch an activity that runs at each place. You launch an activity at each place. And then these activities synchronize, coordinate with each other by using barriers in the middle. And message sends between these guys are happening using the ats that I have mentioned. So you've got enough structure to essentially take any one MPI code and more or less transliterate it into X10 and get it to run. That's fine, but that's not all. The emphasis is, if we were designing just an SPMD language, we would have done it differently. The focus in X10 is to be able to use asynchrony in pretty significant ways. So an example of how you do that is, this is a so-called median computation. Here's the problem. You've got a very large data set, say millions and millions of elements, and you need to find of integers, and you need to find a median. So one obvious thing to do is you go sort this whole array, and then you take the middle element. Okay, but you're sorting a large distributed array, that takes time. So instead, there are algorithms that David Bader, Jaja, and developed, which essentially go along the lines of find medians of medians, and then go use them to divide your data structure in parallel into a set that is below the desired number and a set that is above the desired number. The key point is that there is an iterative loop, and in that iterative loop, there is a fairly interesting pattern of computation going on, where there is recursion, and you keep going out to your nodes to ask them to do some computation, namely find out the number of guys below their median, and then you come back and you compute what is the new median, and you repeat this process until termination. There's actually a more complicated step involved, which is that you've got to rebalance your array. The biggest problem with what I have told you just now is that you may end up with lots of elements in one place that are below the median, and so you don't have parallel computation anymore. So to really get good parallel performance, you need to rebalance this stuff between these places. I'm not showing the rebalance step, but my main point here is that actually this more or less looks like what you would write as a sequential piece of code, but there are a few places where the finished async acts show up, and they do the right, and you can use them to do the right thing. One other thing I'll point out, and this is in the released system, which I'll talk about in just 1 second, but it's not properly documented, but you may find it interesting. This is what we call a collecting finish. And this is an idiom that is inspired sort of by MapReduce. The idea is there are often situations in which what you want to do is spawn some computation in parallel over some data set. Maybe a tree, maybe some kind of a set. And then you want to collect a statistic on that. For example, you're doing n queens, and you're going down this tree structure, and you want to collect one for every node that is a good node. So the idiom here is, of course, you have to use a finish because you're going to do a lot of asyncs, and these asyncs can be going to remote places. But then in the body of this stuff, there's a new statement called an offer, and the offer says, here's a value that I want to contribute. The finish now appears as an expression, not a statement, and it takes a reduction operation plus, which adds the numbers that are coming up. So the mental picture you should have is the finish has spawned a tree of activities. They can generate 0, 1, or more offers. So you really have a sea of offers that are completely unordered with respect to each other. And these offers flow up the chain to the finish. This is the conceptual picture, where they are reduced with this reduction operation, and that result is returned and passed in, and you can store it in a value and so on.
So Vijay, quick question. How would you recommend if someone wanted to accumulate two sums in the collecting finish?
If you want to accumulate two sums, then the straightforward thing is use a type system. So use X, use triples, use quadruples. And then fold them into your offers, and then your reduction operation must work over one.
And you can define your own reduction, right?
Absolutely. These reductions are all used.
Excellent.
Okay. Now, this is interesting. This is in the language, but the reason it's not it's in the implementation, but the reason it's not properly documented at this point is because we're about to move to something much richer. And that's something, this is going to come in the 2.3 version, is called accumulators, or accumulating variables. And sitting back there is Yoav Zivin, who had the privilege of leading a team of undergraduates working in Al Aero's compiler class at Columbia to implement the design of accumulators that we did last fall. So there's a branch in the X10 system which has these accumulator definitions, and roughly speaking, what the accumulators let you do is they let you define new variables. Those are called accumulator variables, and these variables are such that, in fact, you can only, whenever you write to them, you actually reduce the value that's already there with the value that is coming in. So they're accumulating in this. The restrictions on when you can see the value, when you can read the value from the accumulators, and the restrictions are tied to the notion of phased computation, such as within the body of a finish, you cannot read, you can only write, i.e. you're accumulating. Then once it has reached a stable point, i.e. there's only a single thread that is going to be able to access this, now you can read because that's a stable value. So that is another way of dealing with the problem that you raise. You have simply multiple variables and you write into those multiple variables within the scope of your function. All right. There are very good numbers coming out of that program, but before I speak more about numbers, let me go quickly and tell you about our current implementation. So